Hello. With today's lecture, we will start chapter 5, which is on energy. We have finished discussing topics like how far an object will move, what will be its speed, how long will it take to arrive, and these were discussed in chapter 2 and 3, which were on motion in 1 and 2 dimensions. Then in chapter 4, we discussed topics like what is the force acting on the box so as it will move in this direction, calculate the friction force, calculate the acceleration of an object, and these pieces of information tell us how an object will move and why it will move in a certain way. In today's lecture, we will be discussing energy because an object cannot move actually unless it has energy. Let me just give a brief briefing on energy. So there are different types of energies around us. For example, here the solar panels, I think by now everyone is acquainted with them because we are seeing more people installing them on the roof of buildings. Their job is to transfer solar energy, which comes from the sun, we call it solar energy, into electrical energy that can heat our water on the roof of the buildings for shower, or that can electrify our house. So we change solar energy into electrical energy that where we can run our houses, okay, so that we can light up the electric bulbs, we can turn on the washing machine, the dishwasher, all type of electric appliances at home. These cars over here, they also consume energy. The type of energy they take is the gas or diesel, and this is chemical energy, and they transfer it into mechanical energy. That is, the rotor starts moving and then the car will move, okay? So mechanical energy is any energy where moving is included. So the car starts moving, so that's mechanical energy. This lady over here is also running, and in order for her to run, she has to eat some food. So also this is a changing chemical energy, which is in the form of food, chemicals, vitamins, water, and it gets transferred into mechanical energy because again, she's moving. In the case of Billiardo, so the ball comes, we hit it with a certain amount of velocity. It starts moving until it hits a second ball, and this will decide if the ball will enter the hole or not. In this case, we are transferring mechanical energy into mechanical energy because both of them includes moving. The electric fan over here, in order to make it rotate, we need electrical energy. So electrical energy comes to it, and then the fan starts rotating. So we are changing electrical energy into mechanical energy. And in case of the heater, we are changing let's say this is functioning on gas. So this will be transferring gas energy, which is chemical energy again, into heat energy. Okay. In this lesson, we are not actually interested with all of these energies. We are mainly interested with mechanical energy. So we will be focusing on situation like this Billiardo, where we are changing mechanical energy into mechanical energy. And in this lesson, we will learn that mechanical energy itself is divided into certain types of energy. Before I continue, we will start by defining work. Work is energy transferred by a force, okay? So if we have an object and there is a force applied on it, and this force let the object moves a distance delta x, then the work done on the object by this force is Fx delta x, where Fx is the projection of the force F on the x-axis, okay? So this F, we have to define this delta, this x-axis. We define our x-axis, okay? This is x-axis along the motion because this is moving in this dimension. And then the work done by the force on this object is Fx delta x. So it is the work done by force F on the box is W, and this is equal Fx times delta x, the amount of distance the object moved. The units of work is joules. Joules is the name of the guy who worked on in this field. Okay, let's solve exercises in order to see how we use this concept. So Sarah pushes a crate 3 meters along the floor at a constant speed. She pushes with a horizontal force of magnitude 70 Newton. So they're giving us the 3 meters. So this is our delta x, and the force is 70 Newton. How much work does Sarah do on the crate? So the very first thing we do is we define the x-axis. Since it's moving in this way, so the x-axis is horizontal in this way. Okay. Then we see that the force F is all of it on the x-axis. All of force F is on the x-axis. So Fx is F. Okay, so let's remember this. F is on the x-axis implies Fx is equal to F. Okay, so now we come to work equal Fx times delta x. Fx is F times delta x, 70 times 3, 220 joules. Let's do another exercise. A strap inclined upward at a 45 degrees angle pulls a suitcase through the airport. Okay, so this is a suitcase through an airport. The tension in the strap is 20 Newton. So this is actually tension force. How much work does the tension do if the suitcase is pulled 110 meters? So this is the 100 meter is delta x, okay? And the force, the information about the force is that its magnitude is 20 Newton, but it's making an angle 45 degrees with the x-axis. Okay, so the first thing we do is that we choose the x-axis. Since it's moving in this way, because in the airport it's on the ground, it moves in this direction. Then in order to this is F. Okay, so to get x component and y component, I go, this is the x component, and then this is the y component. I am interested in the x component. Fx is equal to F cosine theta, because it's the adjacent. F is 20, theta is 45, so Fx is 14.14. I just plug it in the formula, W equal Fx times delta x, so Fx is 14.14 times how much is the suitcase pulled? It's distance of 100 meters. So we get the answer. So always you choose x-axis along the motion, just as in the case of forces. Let's do one more exercise on work. A drag racer is slowed by a parachute. What is the sign of the work done? Okay, so this guy, he's falling down and there is a force which is slowing him down. Okay, the parachute. If it's slowing him down, then the force is in the opposite direction. Okay, in this case, the force is in the opposite direction and he moves some certain distance delta x. Now, W will be Fx delta x. Again, the delta x, the x-axis passes through the F, but the F is in the negative direction. So the Fx will be minus F times delta x. In this case, the work is negative. So work is negative when the force is resistive force. Example, friction, air resistance. So we get the work to be negative. So not always the work is positive. It's only positive if it's causing the object to move further. But if it is making if it's causing the object to slow down, then it is a resistive. Then the force will be resistive, and in this case, the work will be negative. Okay, so this is about work. Another concept we will learn today is kinetic energy. Kinetic energy is when an object is in motion, okay? So if an object of mass m, moves with a speed v, then it has kinetic energy by definition, Ke, so kinetic energy is Ke, it's half mv squared. So let's look at this person. She's running, so she has a speed and she has a mass, so she has kinetic energy equal half mv squared. This ball, it's moving with a certain speed and it has a mass, so kinetic energy is half mv squared. This baby is moving with a certain speed, perhaps it's very slow speed, and it has a mass, then kinetic energy we applied is half mv squared. So any object of mass m moving with a speed v has kinetic energy. By definition, kinetic energy is half mv squared. Okay, this we need to memorize these concepts. The unit of energy is also joules. So work and energy have similar units. Let's do this exercise. A car of mass m equal 1,000 kilograms speeds up by 5 meters per second, starting from 5 meters per second. So V initial was 5, V final was 10. Another situation, the same car speeds up by 5 meters per second, starting from 10. So V initial is 10, V final is 15. Calculate the increase of the kinetic energy in the first situation. So the increase of kinetic energy is delta kinetic energy. It's kinetic energy final minus kinetic energy initial. This is half mv final square minus half mv initial square. Instead of m, I put 1,000. Instead of v final, it's 10. V initial is 5, and I get the answer. Then calculate the increase of the kinetic energy in the second situation, and I do the same thing. So just remember, increase or decrease in a quantity is delta quantity. Okay. Okay. So if they ask me calculate the increase in the velocity, so this will be delta velocity. Okay. So this is information you need to keep in mind. So now we know that W work is Fx delta x, where the x-axis we take it along the line of motion. Kinetic energy is half mv squared. And now we will learn about potential energy. Potential energy is divided into two energies in this chapter. The first one is gravitational potential energy. If we look at this, it's due to heights. So this rock over here, it's not moving, okay? It's not moving, it's standing still, but it has the potential to fall. It has the potential to fall down if we give it a push, for example. So this object, although it's not moving, but it has the potential to fall, and due to its height, so if it falls, it will fall because of its height, then it's called gravitational potential energy. There is something pulling it downward, but it's not moving because it's standing still on this mountain. But if we give it a push, it can fall down. Elastic potential energy, it's due to stretched or compressed strings or springs. So again, this bow, for example, and the arrow, if I just pull the arrow, it can stand still, but if I leave it, it will have the potential to move. Okay, it will have the potential to move. So potential, what in English is something that can change into. In Arabic, we say عنده إمكانية to do something. Okay, so for example, if a little boy can draw very nicely, we say he has the potential to be an artist. Okay, if a girl has a very nice sound, so we say she has the potential to be a singer. You see, so this rock over here, it's standing here, but we can see that if it slips, it can move and can starts having velocity. That is, it can have kinetic energy. Right now, it doesn't have kinetic energy, but if it moves, it starts having kinetic energy. So it has the potential to have kinetic energy. That's why it's called potential energy. Okay, so we have two types of energy, potential energies. One is gravitational due to gravity. So once it is left, once it is allowed to move, gravity will pull it downward. And this is due to the rope or to the string or to the spring because they are compressed. So it has elastic potential energy. Okay, let's do exercise. This is gravitational potential energy. An object of mass m at an altitude h has gravitational potential energy like these two skiers. Okay, GPE, you memorize it. It's m, which is the mass, times g, which is the gravity, times the h, which is the height. Okay, so these both skiers have the same mass, but the blue skier, as we see, is higher than the yellow skier. Then GPE of the blue guy is higher than the GPE of the yellow guy. Okay, so gravitational potential energy, we refer to it by GPE. Now, the other example, the yellow and the green are at the same height, but the green one is heavier. In this case, the green skier will have higher GPE. So if these two guys fall, the green one will possess more energy. He can go much longer distance. And in this case, the same thing, the blue guy will go a longer distance because he has higher GPE. Let's solve an exercise on that. Competitors climbed a total vertical distance of 320 meters. How much gravitational potential energy does a 70-kilogram racer gain during race? Okay, so it's asking about gravitational potential energy, which is the GPE. So GPE is equal mgh. M is the mass of the guy, so that's 70, times g, which is 10, times the vertical distance h is 320, and then we get GPE is equal to this. So in order to solve any problem with the GPE, we have to say, what is the reference? So the object, let's say the reference is where he's standing here, the ground. Then when he goes up, he starts having GPE equal mgh because now he's at an altitude 320 from this reference, okay? However, for example, if we take the reference to be up here, then if we calculate the GPE, it will be 0 because up here, the height is where he's standing, the height is 0 from the reference point we are taking, okay? So to calculate the GPE, we always need to refer to a reference. Elastic potential energy, so it happens if we have a spring or a rubber band or an arrow. If it's at equilibrium, there is no elastic potential energy, it will be 0. However, if it's compressed or elongated, then it has EPE equal half K delta X square, where K is the spring constant that we learned in Hooke's law when we learned that T equal K delta X, right? So T equal K delta X, this is the K that comes in this formula. So delta X is how much the object is compressed or elongated. The same thing here, if it's unstretched, there is nothing. However, if it's stretched, then we start having EPE equal half K delta X square. Once it's released, there is no elastic energy anymore. So elastic potential energy is transferred to the stone as kinetic energy, because once I leave it, the stone will go. So it will start moving. So it will, the energy of the stone will change from EPE to kinetic energy. Let's do an exercise. An archer pulls back the string on her bow to a distance of 70 centimeters. So I have delta X equals 70 centimeters from the equilibrium position. To hold the string at this position takes a force of 140 Newton. So this is the tension, because this is, you can call it F, you can call it T, but it's nice to call it with names we already know it. So it's the tension, because there is a rope or a string, it's 140 Newton. So how much elastic potential energy is stored in the bow? We say EPE is equal half K delta X square. We want to calculate this value. So delta X, we know it's 70 centimeters, but we don't know K, okay? We have T, so we try to solve T equal K delta X. K is equal, we have the T, it's 140 divided by delta X, which is 70 centimeter, we change into meter. We get the K to be 200 Newton per meter. We plug it in this formula, half K delta X squared, and we get EPE is equal 49 joules. Okay, so today's lecture was all definitions, and all these formulas that I defined, we need to memorize them. So in short, we have W is equal to the work done by an object. So the work done by a force on an object is equal to work equal Fx delta X. Okay, kinetic energy, we refer to it by KE. KE KE equal half mv squared. So it's only there when there is a speed, when the object is moving. Then gravitational potential energy GPE is mgh. So it's only there if there is height, if an object is at an altitude. And finally, elastic potential energy E is equal half K delta X squared. So it only happens when there is compression or elongation. So when there is delta X. Okay, these formulas are to be memorized, and we will be using them next week as we start by mechanical energy. Okay, tomorrow's session will be a revision for the exam, and tomorrow's live session will be to take questions if you have any questions regarding the exam. If you don't have any questions regarding the exam, tomorrow's live session, there will in tomorrow's live session, then it will be a very short session. So I advise you to prepare questions so as you can ask me before your exam. That's it for today. Good luck.